Have you ever looked at the surface of a lake and wondered how deep it actually goes? Not the number on a map, but the real answer. Because there are places on this planet where that question has no satisfying reply. Lakes that discharge tens of millions of liters of water every single day with no visible source. Flooded caves where the world's most advanced robots descended over 400 meters and still found nothing beneath them but more darkness. Lakes that fooled one of the greatest scientific minds in history with a bottom that wasn't really there. These places are called bottomless, not as folklore, not as exaggeration, but because every serious attempt to find solid ground in them has ended the same way, with more questions than measurements. Behind their deceptively calm surfaces lie vertical shafts, branching underwater labyrinths, and geological structures that drop into the earth further than any cable or sonar beam has yet confirmed. Today, we examine only verified facts about how these natural anomalies actually work, and why modern deep-sea ROVs, magnetic sensors, and sonar equipment still cannot give us complete answers. This is a story about what hides beneath the water we thought we understood. Right now, at this exact moment, beneath the surface of lakes and mountains on every inhabited continent, water is moving through passages that no human being has ever seen. Not slowly, not as a gentle underground seepage through soil, but as pressurized rivers operating under loads measured in tens of millions of liters per day, carving through networks of dissolved rock tunnels and chambers that stretch for kilometers in every direction beneath terrain we have mapped, named, and assumed we understood. The scale of this hidden architecture is genuinely difficult to absorb. Lake Tserik-Kel in Russia's Caucasus Mountains glows an impossible neon blue and discharges 70 million liters of water every single day through an underwater labyrinth whose full extent no researcher has yet charted. A lake in the Moscow region produced depth measurements so inconsistent that Dmitri Mendeleev, the chemist who constructed the periodic table of elements, walked away from it without a satisfying explanation. In Slovenia, an entire lake fills and drains on an annual cycle, its water vanishing through karst sinkholes into underground rivers that discharge into the Adriatic Sea 50 kilometers away. And in the Czech Republic, the world's most sophisticated deep-sea ROVs descended to a record depth of over 400 meters and still couldn't locate the floor. In this investigation, we will follow the water downward, through the branching underwater labyrinths of Tserik-Kel, through the phantom depths of a Moscow region lake that wore a false bottom like a disguise, through the communicating vessel systems that link lakes across entire mountain ranges, through natural hydraulic valves, and into the Hranice Abyss, where sonar data suggests a total depth that no machine built by human hands has yet reached. We will examine the technology deployed against these mysteries, from 19th century weighted ropes to modern remotely operated vehicles, and we will confront the zones of silence, where magnetic anomalies and extreme underwater pressure disable electronics and return data that contradicts physical reality. Because what ongoing research is uncovering about the underground architecture of this planet is not a collection of isolated geological curiosities. It is evidence of a global system, ancient and vast, operating according to physics that we are only beginning to formally describe. And what's happening right now, in caves and beneath lakes that most maps don't acknowledge, is rewriting everything we thought we knew about the ground beneath our feet. Picture a lake so impossibly blue that every photograph taken of it gets flagged as digitally enhanced. Tourists who visit Lake Tserik-Kel in the Kabardino-Balkaria region of Russia describe the same moment of disbelief, standing at the edge, staring into water that glows with a neon turquoise luminosity that shifts between cerulean and electric blue depending on the angle of the sun. The lake sits at 1,169 meters above sea level in the Caucasus Mountains, surrounded by terrain that freezes hard every winter. Yet the surface of Tserik-Kel never ices over. Its temperature holds steady at approximately 9 degrees Celsius year-round, at every depth, regardless of the season outside. That alone is unusual enough to warrant investigation. But when hydrologists began measuring the volume of water leaving the lake each day through its outflow into the Tserik-Balkarian River, they recorded a figure that defies straightforward explanation. Approximately 70 million liters discharged every single day. 70 million liters per day from a lake, covering just 2.6 hectares of surface area. With no visible rivers feeding into it, no significant tributaries, no obvious precipitation source capable of replacing that volume. The math doesn't balance. Soviet geologists first attempted to resolve this contradiction in the 1980s, when a team of divers conducted the first systematic investigation of the lake bed. What they found at approximately 35 meters depth wasn't a bottom at all. It was an opening. A karst sinkhole, the product of thousands of years of underground limestone dissolution, dropping further into the mountain's interior. A karst sinkhole is not simply a hole in the ground. It is the visible terminus of an entire architectural system, a branching network of dissolved rock passages, chambers, and underwater labyrinths that can extend for kilometers in every direction beneath the surface, connecting to pressurized aquifers carrying water from sources that may originate dozens of kilometers away. This is where Tserik-Kel's impossible water budget finally makes sense. The lake is not a container. It is a valve on top of a vast subterranean hydraulic system embedded deep within the Caucasus Range. The lake's signature color is itself a clue. High concentrations of hydrogen sulfide combined with dissolved minerals, characteristic of deep karst systems, produce that otherworldly blue, the same chemistry that makes the photographs look manipulated. According to data compiled by the Institute of Geography of the Russian Academy of Sciences, the maximum confirmed depth of Tserik-Kel exceeds 258 meters, but that figure represents only what modern equipment has been able to measure before the lateral cave passages become too narrow or too complex to follow. The true lower boundary of the underground labyrinth system remains unknown. What researchers have confirmed is that the cave branches sideways, not just downward, spreading beneath the mountain in directions that no diver has yet mapped completely. Tserik-Kel is not a geological oddity. It is a window into a hidden plumbing network that operates on a scale most people never imagine exists beneath the ground we walk on. But if this lake stuns with raw power and visible spectacle, another lake, far less dramatic on the surface, managed to confuse one of the greatest scientific minds in Russian history. It sits quietly in the Moscow region. Dmitri Mendeleev himself studied it, and he left without an answer. There is a lake in the Moscow region that looks, at first glance, like thousands of others scattered across the Russian landscape. Calm, unremarkable, fringed with reeds and birch trees. Lake Tserik, near the town of Solnechnogorsk, draws weekend visitors and amateur fishermen who have no idea they are sitting above one of the most persistently puzzling hydrological mysteries in European Russia. The legend attached to this place is old and consistent. Local fishermen have been claiming for generations that the lake has no bottom. Drop a weighted line, and it simply keeps descending. The story attracted the attention of Alexander Blok, the celebrated Russian symbolist poet, who lived near the lake in the early 20th century and referenced its strange, unresolvable depth in his private correspondence. More significantly, it attracted the attention of Dmitri Mendeleev, the chemist who constructed the periodic table of elements, who visited Tserik as part of a broader investigation into Russian lake systems and reportedly came away genuinely unsatisfied with the available explanations. When a man whose entire intellectual framework was built on systematic measurement encounters something that refuses to be measured consistently, that is worth paying attention to. What Mendeleev encountered, and what modern limnologists have since analyzed in detail, is a phenomenon called a false bottom. In Russian scientific literature, ложное dno. A false bottom is not a myth or a misperception. It is a real, physically measurable layer suspended within the water column, composed of a dense accumulation of decomposing peat, fine silt, particulate organic matter, and trapped gases that together form a semi-solid membrane at a certain depth. This layer behaves in a deeply counterintuitive way. It is buoyant enough to support its own structure, opaque enough to block sonar returns and light penetration, and physically substantial enough that a weighted measuring line will stop on its surface and register a reading. A perfectly convincing bottom that is, in reality, floating several meters above the actual lake bed. The fishermen weren't wrong. Their lines were genuinely stopping. They simply weren't reaching stone. Lake Tserek's false bottom forms because its basin was historically fed by peat-rich marshland, and centuries of organic accumulation have built up a suspended layer dense enough to fool both human observers and early measurement technology. But here is what makes the false bottom phenomenon genuinely strange rather than simply explainable. The layer moves. Seasonal temperature changes, shifts in water pressure, storm events and variations in methane gas production from the decomposing organic matter all cause the false bottom to rise or sink within the water column, sometimes by several meters over the course of weeks. This means that the same lake, measured twice by different observers a month apart, can produce entirely different depth readings from the same location. Mendeleev's frustration begins to make complete sense. He was working with 19th century measuring equipment against a target that was physically relocating itself between visits. Modern researchers using calibrated sonar equipment have since established that Lake Tserik-Kel's actual stone and sediment bottom sits at a maximum depth of around 15 meters. Not spectacular by any global standard, but the false bottom layer frequently presents at depths between 5 and 10 meters, creating a phantom geography that the lake wears like a disguise. What makes this more than a local curiosity is the question it raises about every other bottomless lake report throughout history. How many of those legends were, in fact, someone's weighted line resting on a floating membrane of compressed organic matter, hovering above a very real, very reachable bottom? But the false bottom only explains lakes that deceive through organic chemistry. There is an entirely different class of lake, one where the depth is real, the water moves in volumes that should be impossible, and the explanation involves something engineers call a hydraulic valve. And when you understand how that system actually works underground, the legends stop being legends entirely. In 1848, a Hungarian physicist named Hranice Abyss demonstrated a principle in his Budapest laboratory that most school children encounter in basic science class and immediately forget: communicating vessels. Two containers connected by a tube at the base will always equalize their water levels, regardless of their individual shapes or sizes. Pour water into one side and the other side rises. Drain one container and the other follows. The principle seems almost embarrassingly simple until you scale it up by a factor of several billion and apply it to the interconnected lake and aquifer systems that run beneath entire mountain ranges, continental shelves, and ocean floors. At that scale, the communicating vessels principle stops being a classroom demonstration and starts being the operating logic of a planetary hydraulic machine. Hydrologists studying karst terrain, the limestone and dolomite landscapes where underground dissolution creates cave systems and sinkholes, have documented lake pairs and lake clusters separated by dozens of kilometers of solid rock that nevertheless respond to each other's water level changes within hours. Drain one and its distant partner drops, flood one with dye traces, and that dye emerges from springs and lake outlets far beyond any visible surface connection. The mechanism that makes this possible at the most dramatic scale is what geologists call a hydraulic valve, Gydravlichesky klappen in Russian scientific terminology, and understanding it requires abandoning the mental image of underground water as a slow, diffuse seepage through soil. In mature karst systems, water doesn't seep. It flows through conduits, carved limestone tunnels, sometimes meters in diameter, operating under pressure like pipes in a municipal water system. These conduits are not static. They are dynamic structures shaped by geological stress, seasonal pressure changes, and the enormous weight of overlying rock. A hydraulic valve forms when a conduit's geometry creates a pressure threshold. Below a certain water volume, the passage remains sealed by its own geometry or by trapped air pressure. Above that threshold, the seal breaks, and the system discharges with sudden dramatic force. This is why certain lakes in karst regions are documented to drain almost completely overnight, not because of catastrophic geological failure, but because a natural pressure valve somewhere in the connected underground network reached its opening threshold and released the accumulated hydraulic load. The documented cases of this phenomenon are extraordinary in their specificity. Lake Tserik-Kel in Slovenia, studied systematically since the 17th century by natural philosopher Johann Weichard von Valvassor, who described it to the Royal Society of London in 1689, fills to a lake of approximately 26 square kilometers during wet seasons, and then drains almost entirely within weeks through a network of karst conduits feeding underground rivers that eventually discharge into the Adriatic. The entire cycle repeats annually, with enough regularity that local communities historically farmed the lakebed during its dry phase and fished it during its flooded phase. Von Valvassor's description was so precise and so apparently impossible to a 17th century scientific audience that the Royal Society initially struggled to accept it as factual reporting rather than travelers' exaggeration. Modern hydrological mapping has since confirmed every detail he documented, adding the further discovery that the Hranická system connects underground to cave networks extending over 50 kilometers in multiple directions, all operating as a single interconnected hydraulic machine governed by natural valves responding to seasonal precipitation loads. The underground plumbing of this planet is not a collection of isolated curiosities. It is a system, ancient, vast, and operating according to physics, that human engineers only began to formally describe in the 19th century. But if communicating vessel systems across Europe represent one category of underground mystery, there is a place in the Czech Republic where the system goes so deep and the cave extends so far beyond the reach of any technology deployed against it that the world's most sophisticated robots ran out of cable before they ran out of cave. And sonar suggests they hadn't even reached the halfway point. In September 2016, a team of researchers from the Czech Speleological Society lowered a remotely operated vehicle, a deep-sea ROV, into a flooded cave in the Moravian region of the Czech Republic. The cave is called the Hranice Abyss, or Hranická propast in Czech, and it sits inside a nature reserve near the small town of Hranice, largely unknown outside specialist geological circles until that September afternoon. The ROV descended through water that shifted from pale turquoise to absolute blackness as depth increased. At 200 meters, it was still descending. At 300 meters, the team on the surface began managing cable tension carefully. At 404 meters, the cable ran out. The robot was still suspended in open water, its lights illuminating nothing below it, but more darkness extending beyond the reach of its cameras. The Hranice Abyss had just officially become the deepest known flooded cave on Earth, surpassing the previous record holder, the Pozzo del Mero in Italy, by a significant margin. But the genuinely unsettling part of that record is not the 404-meter measurement. It is what happened when researchers pointed sonar equipment downward from that depth and tried to find the bottom acoustically. The sonar returns from the Hranice Abyss have been analyzed by multiple independent research teams since 2016, including geologists from Masaryk University in Brno and international cave diving specialists. The acoustic data consistently suggests that the cave continues well beyond the 404-meter point reached by the ROV. Current estimates based on sonar profiling place the probable total depth at somewhere between 800 meters and 1.2 kilometers, making the flooded portion of the Hranice Abyss potentially deeper than some sections of the Grand Canyon measured from rim to river. The cave formed through a karst sinkhole process operating over an estimated 2 million years. With the dissolution of Devonian-era limestone, rock laid down approximately 380 million years ago, creating a vertical shaft of extraordinary dimensions. The water filling it is thermomineral, unusually warm for its depth, chemically distinct from surface groundwater, and bearing the signature of deep geological sources that connect the cave system to hydrothermal circulation far below the normal water table. This is not rainwater that filtered down through soil. This water is rising from below, driven upward by geothermal pressure through conduits in the underlying aquifer system. The same communicating vessel mechanics operating on a geological rather than hydrological timescale. What researchers find particularly significant about the Hranice Abyss is not simply its depth, but the implication of its geometry. The cave's shaft is predominantly vertical, which means that whatever connected underground labyrinth feeds its thermomineral water supply extends horizontally at depth, spreading outward beneath the Moravian landscape in directions that surface investigation cannot map. Czech geologist Pavel Bosak, who has studied the site extensively, has noted that the Hranice system likely represents only the most accessible vertical entry point into a far larger horizontal cave network operating at depths that current technology cannot directly investigate. The 404-meter ROV descent, remarkable as it was, explored what amounts to the entrance hall of a structure whose true dimensions remain entirely unknown. The world record stands, but it stands with an asterisk. We know the Hranice Abyss is at least 404 meters deep. We do not know how much deeper it actually goes. We simply ran out of cable. And this is the problem that defines the entire frontier of underwater cave exploration. Not the darkness, not the pressure, not even the distance. The limiting factor is consistently the technology. Except that in certain locations around the world, even the most advanced technology encounters something stranger than a physical limit. It encounters places where the electronics simply stop working, where sonar returns nonsense, where magnetic compasses spin freely, where robots descend into what researchers have begun calling, with careful scientific reluctance, zones of silence. For most of human history, measuring the depth of a lake or underwater cave meant a rope, a heavy weight, and a person with steady hands paying outline until tension changed. This was the technology Mendeleev used at Seneš. It was the technology 19th century naval surveyors used to chart ocean floors, producing measurements that were sometimes accurate, sometimes intercepted by false bottoms, and sometimes simply wrong because the rope drifted with subsurface currents and registered oblique distance rather than true vertical depth. The transition from rope and weight methodology to modern sonar-based acoustic measurement in the mid-20th century, seemed to resolve most of these problems permanently. Echo sounders send a pulse of sound downward, measure the time it takes to return from a hard surface, and calculate depth with a precision that human rope handling could never achieve. Then came remotely operated vehicles, ROVs or TNPA in Russian technical terminology, beginning with early military prototypes in the 1960s and evolving through decades of engineering refinement into the sophisticated robotic platforms capable of descending to the Hranice Abyss's 400-meter threshold in 2016. The technology appeared to have finally given researchers the tools to answer every remaining question about underwater depth and geology. Then certain locations began producing data that the technology was not designed to process. The phenomenon that cave researchers and deep lake investigators began documenting with increasing frequency from the 1990s onward resists comfortable classification. In specific underwater locations, clustered particularly but not exclusively in areas of intense karst geology, volcanic substrate, or documented geomagnetic anomaly, ROV systems experience what their operators describe as instrumentation failure that cannot be attributed to pressure damage, cable fault, or manufacturing defect. Magnetic compasses aboard the vehicles spin or lock in directions that correlate with no known magnetic reference. Sonar systems return readings that contradict the physical geometry of the space the ROV is visibly occupying. Distances that don't match camera footage, echo returns, arriving from directions where no surface exists. In the most extreme documented cases, vehicles lose navigational orientation entirely, their onboard computers registering positional data that places them outside the physical boundaries of the cave system they entered. Researchers investigating the hydrothermal cave systems beneath Lake Baikal, the world's deepest freshwater lake at 1,642 meters, have reported sonar anomalies in specific basin sectors that produce consistent, repeatable, incorrect depth readings that differ from physically verified measurements by margins of up to several hundred meters. These are not instrument malfunctions in the conventional sense. The instruments are functioning. They are simply receiving information that doesn't correspond to physical reality, as measured by independent methods. The scientific explanation that has gained the most traction among geophysicists studying these zones of silence, zoni molchenia, a term borrowed originally from anomalous radio dead zones in northern Mexico, but now applied more broadly to any location of consistent multi-system instrumentation disruption, centers on localized magnetic anomalies produced by specific mineral concentrations in cave and lakebed geology. Magnetite deposits, formations of basaltic rock with unusually high iron content, and certain configurations of hydrothermal mineral precipitation can generate localized magnetic fields intense enough to interfere with electronic navigation systems, distort acoustic wave propagation, and in extreme cases induce measurable electrical currents in the metallic housings of ROV equipment. Dr. Alexei Soroktin of the Institute of Oceanology of the Russian Academy of Sciences has documented magnetic field intensity variations in deep Baikal Basin sectors that exceed expected background measurements by factors of up to 40, variations sufficient, he argues, to account for the navigational anomalies reported by ROV operators working in those areas. The extreme pressure at depth compounds these effects. Water compressed beyond a certain threshold changes its acoustic transmission properties in ways that standard sonar calibration does not account for, producing the phantom readings and impossible geometries that operators interpret as malfunction. What these zones of silence ultimately represent is not a supernatural phenomenon and not a failure of science. They represent the frontier condition of any genuine investigation. The places where our instruments reach their limits are precisely the places where the most important questions are still waiting. Researchers continue to develop pressure-resistant, magnetically shielded ROV platforms specifically designed to operate in anomalous field environments. The Hranice Abyss awaits a cable long enough. Lake Baikal's deepest basin sectors await instrumentation robust enough to return clean data from inside the magnetic interference zones. And somewhere beneath the Caucasus Mountains, the branching underwater labyrinths of Tserik-Kel continue discharging 70 million liters per day through passages that no human being has yet followed to their source. What connects a glowing blue lake in the Caucasus Mountains, a Moscow region lake that confounded Mendeleev, a Slovenian lake that empties itself every year, and a Czech cave that swallowed 400 meters of ROV cable without revealing its floor? Not folklore, not exaggeration, physics. The same communicating vessel principles that a Hungarian physicist demonstrated in a Budapest laboratory in the 19th century govern the movement of tens of millions of liters of water per day through karst conduits beneath entire mountain ranges. The same hydraulic valve mechanics that drain Lake Hranice annually have been operating beneath the European landscape for millions of years. The false bottom that fooled generations of fishermen at Senej is not a mystery. It is organic chemistry, behaving exactly as organic chemistry should, suspended in a water column that no one thought to analyze carefully enough. And the zones of silence that disable ROV electronics in the deepest flooded caves are not anomalies in the supernatural sense. They are the predictable consequence of magnetic field intensities and pressure gradients that our instruments were not originally designed to handle. But here is what matters beyond the individual explanations. Every one of these locations was considered unsolvable until someone looked at it with better tools and more precise questions. The Hranice Abyss held its record depth for decades simply because no one had built an ROV capable of descending that far with enough cable to reach it. Terrakel discharged its impossible 70 million liters per day for centuries before karst hydrology gave us the vocabulary to describe what a branching subterranean aquifer system actually does. The zones of silence that still defeat modern instrumentation are not permanent mysteries. They are the current edge of what our technology can reach. And the edge moves. It has always moved. Every generation of researchers has pushed it further downward, further into the dark, further into the passages that the previous generation believed were simply too deep, too complex, or too anomalous to investigate productively. The underwater labyrinths are still there. The hydraulic valves are still operating. Somewhere beneath the Caucasus, beneath Moravia, beneath the Slovenian karst, the global plumbing system is moving water through passages no human eye has seen, and the cable for the next ROV descent is already being manufactured. The bottom exists, we simply haven't reached it yet. If this investigation into the hidden architecture beneath our lakes and caves left you with more questions than you started with, that's exactly where the best science begins. Like this video if it changed how you think about the ground beneath your feet, subscribe so you don't miss the next investigation, and watch the video appearing on your screen right now, because what we uncovered there connects directly to what you just learned here.